Jolly good. So that's broadly the people. I haven't mentioned the PhD students. There are many, and obviously, as ever, they do the bulk of the work, for which I am taking credit at this point. So research areas really, well, right across the thermal hydraulics theme, core and plant fluid flow generally, natural circulation, multi-phase flows, boiling in particular, DMB, CHF prediction, and also interest in liquid metal flows and magnetohydrodynamics, so particularly high magnetic field magnetohydrodynamics. To address those areas, we were interested in a range of techniques, CFD, including DNS, but turbulence models in particular, reduced order models. I think many on this call won't have the facilities that Elia was discussing. I wish we had. Magnetohydrodynamics and isogeometric methods as well, methods that we've taken from some of our work in neutronics. Multi-phase CFD, Eulerian approaches and interface tracking methods, systems and sub-channel codes, so that sort of 1D type approach for entire plant and core analysis. Code coupling, particularly between CFD and systems and sub-channel codes. And across all of that, really, uncertainty quantification plays an important role. And we're funded through a number of mechanisms, not in any particular order, but we're heavily involved, as others on this call are, with the EPSLC Indo UK activities. We're obviously involved in the CDTs. We host the Rolls-Royce Nuclear UTC, the Imperial College under that anyway. We have activities in the SMR program for Rolls, and we also have activities and funding through a few others mentioned there, UKAEA, NNL, Fraser-Nash, and a few others. So just a couple of very brief ones I don't want to go over. Boiling modelling, this is some of the work that I mentioned Giovanni Giustini involved in. This is really looking at very detailed modelling of boiling from inception through to growth and detachment. And that's an activity that we're coupling with molecular simulations of the processes near the surface through to the continuum level, and really looking at the effects of surfaces on that. So we're really coupling the materials almost with the fluid processes. So that's a big and growing area that builds on a lot of our boiling work that we've done over many years. UQ, uncertainty quantification, that's another big activity that covers quite a lot of what we're doing now and is growing. Gaussian process regression methods, Bayesian calibration for determining constants. Whatever we're doing, certainly unless we're doing DNS, then constants are involved. So determining those and quantifying uncertainties in turbulence models, and a whole host of work involved in UQ. I'm only picking one or two of the things. I'm not going to go through a whole list. Reduced order methods, again, if we haven't got vast supercomputing resources, then the requirement, our approach, if you like, this side of the pond, is looking at reduced order methods, particularly pod-based methods, where we take full order models and we do a proper orthogonal decomposition to reduce the cost at some limitations, obviously, and we've done a lot of work on that in collaboration with a group in Italy, Trieste. And I think I'll end it there. There are obviously others, but I think 5 minutes. I think that'll do, if that's okay. I don't know if I need.
Yeah, thank you, Mike.
Okay.
Yeah, you can stop sharing. Then the next one can share his screen. Yeah. The next one is Marco from Leeds University.
Okay. Good morning, everyone. Let me share my screen. Can you see it?
Yeah.
Okay. So yeah, we'll try to go on a brief overview of the thermal hydraulics activity at the University of Leeds. First of all, that is part of the Nuclear Engineering Group, which is based in the School of Chemical and Process Engineering, but is a really multidisciplinary team that has expertise other than in thermal hydraulics, also in decommissioning, decontamination, waste management, and in advanced fluid cycles, and has been funded with several grants from the UK and also Europe, present and past. So with regards to the thermal hydraulics activity, most we use computational fluid dynamics to advance our modeling capabilities in different aspects of nuclear thermal hydraulics, and our main expertise are in multi-phase flows, in particular gas liquid, but also gas or liquid with solids, and specifically also on bubbly flows. And I will show some results on those. Then the other area in multi-phase flows where we really focused on in boiling, and also we apply CFD to natural convection and passive safety systems in the context of nuclear thermal hydraulics. The software we use are mainly StarCCM+, OpenFOAM and NEC 5000. Those are the software we are experienced on, and the activities have been funded through different EPSRC grants, mainly on the UK-India civil nuclear collaboration, and also the fellowship that I currently hold. So with regards to bubbly flows, we are interested in modeling those in the context of nuclear, because they are a fundamental part of the boiling process, but also because they are relevant in many other sectors where we require mixing, and that is also a fundamental part of some reprocessing techniques. We use different techniques to model bubbly flows. We have capabilities with multi-fluid models, so Eulerian models, mainly using StarCCM+ and OpenFOAM, but also we use Lagrangian tracking, and this has been done mainly for macrobubbles, and we are developing also capabilities in using interface resolving methods such as the volume of fluid, and you can see some example on the right of a single bubble rising in a channel, and also of some multiple bubbles simulation. This is one of the recent developments. So the development of also in the area of multi-phase gas liquid flows, the development of a generalized multi-phase model that is called GEMMA, that's tied to go beyond the fact that in gas liquid flows we have multiple flow regimes, and most of the time the models at the present time are limited to some of those. So what we are trying to do is maintain the resolution of dispersed bubble or droplets with average methods such as the multi-fluid. So it's a multi-fluid framework, and on top of those we have the resolution of the large interfaces only, more than resolution, let's say, keeping the interface sharp and trying to apply the right closure relation. And on the bottom right, there is an example of the simulation of an horizontal pipe. So on the left, the flow is dispersed with many bubbles, and then the void fraction gets higher on the right, and the model starts to detect large gas structures, and it becomes a plug and then a slug flow. The shape is a bit strange, but that's because the pipe is scaled in the flow direction, so it's much longer than how it appears. Other than that, we had many activity in boiling. Again, the interest is, of course, the prediction of boiling heat transfer and the CHF in the reactors. What we do is we try to develop more physically based models of the boiling process, in particular for the growth of the bubble and the departure, and implement those in CFD, and have simulation of boiling flows in nuclear thermal hydraulics. Some of those are in natural circulation, and this is the other area we are active on, is the passive cooling. So the use of CFD, mainly coupled with large eddy simulation to predict passive cooling and the effectiveness of passive cooling in nuclear reactor. You see two examples here, the cooling of the outside of a cylindrical vessel in a water pool in case of core melting, and also on the right, the simulation of a natural circulation loop with distributed heat generation. So here the focus is the molten salt reactor, again, done with large eddy simulation. This is on the right, single phase instead. On the left, in the external reactor vesicle, we also had some boiling on the outside surface. So thank you very much. That was my presentation.
Thank you, Marco. The next one is Marcus from Bangor University.
Yeah, good morning all. I'll try to share here. So let's see if, can you see my screen?
Yeah, yes.
To get it started as a proper slideshow as well. Let's see if it will work. Yes, okay. Yeah, so I'm Marcus Dahlfors, representing the Nuclear Futures Institute of Bangor University. We're pretty fresh on the arena here in nuclear thermal hydraulics. And I want to present to you the background, roughly how our institute has reprofiled itself lately. So currently, or let's say we have a fairly solid base within materials, waste forms, fuel manufacture and design, and fuel performance. What I'm bringing to the group is reactor physics and thermal hydraulics, and yeah, probably a little bit of dabbling into the areas of fuel performance and monitoring and control as well. So we are forming a fairly complete group. By the way, for those who are not exactly familiar where we are, you see a small map there which points out Bangor and some of the sites for nuclear development that we have in the area. We're funded by a 6.5 million pound Cymru grant, and this is running actually now after a reprofile of the funding. It's running until 2023. We're right now 5 academics and 7 researchers, but will be expanding quite significantly, as I will show you on the next page. We have some new and refurbished lab space. What concerns thermal hydraulics, I'll show you. And then we have quite significant materials laboratories and actually more proposals in the making on that side as well. The one that we have right now is Merlin, which is a refurbished, quite sizable lab where we can even handle active materials. The recruitment wave that we are initiating right now is fairly significant. There will be more information if you go to our web page. I'm quite aware of the time limitation, so I will just tell you what will affect the area of that I'm active in myself. So I'm looking towards engaging 1 to 2 lecturers in reactor physics and thermal hydraulics, and also control and instrumentation, which will be relevant to the field of thermal hydraulics experimentation. That's where I think our group is fairly complementary to many other groups in the UK, although I know there are others who are active in experimental TH, but we are quite focused on that part of thermal hydraulics. Then we're also looking to engage at least three postdoctoral research associates in these areas as well. Quite importantly, we're getting a couple of technicians in as well, which will be quite significant for the current thermal hydraulics experiment project that we have going. It's the Thor facility, a thermal hydraulics open access research facility. We would very much welcome anyone who wants to come and design experiments and carry out on our rigs. And I would refer to said web address, and please don't hesitate to get in touch if you have ideas. This rig, there's a very simplified diagram to the right showing what it's roughly about. There are a few things missing there, but it is right now in detailed design, and construction is to begin next month. We have done some initial procurement and are well on our way. But I want to turn my focus to actually a proposal due to the recent National Nuclear User Facility call, the phase 2A of it. We have developed actually an upgrade proposal. So Thunder, which is the Thermo Hydraulics upgraded and enhanced research facility. And this would basically build on a similar concept, but where we would take up pressure to 80 bar with a very special feature of a pressure chamber that can accommodate large window access to thermal hydraulics experiments inside of it. For geometries of quite significant extent, we are looking to maybe a 2.5 meter high and 1.2 meter pressure vessel where we would have pressure equilibrium and therefore could run thin windows or thin wall geometries where you could apply CT techniques, computed tomography. 80 bar, we would reach 295 degrees. You can read about, well, I think you can figure out what kind of potential experiments you could do. This is the basic scheme of the loop that we are proposing, and especially the system here with the pressure tank and the pressure equilibrium condenser is quite bespoke to this. And it requires an inert atmosphere of nitrogen to be run. It has generated a bit of interest, and actually I've spoken to some people within the UKAEA SIG network and who are also interested. There are also other complementary concepts out there for the next for this call, but and many things look interesting, but this is now ours, and if we're successful, we would obviously look for collaborators and yeah, people with suitable problems to test in this kind of facility. How are we doing for time?
Yeah, I hope to. Yeah, thank you. Thank you, Marcus.
Okay, I'm happy with that. Yeah. So if you have questions, don't hesitate to contact me later.
Yeah, thank you. The next one is David Emerson from STFC Daresbury Laboratory. Marcus, can you stop sharing? So
yeah, I will. Just that my screen it disappeared. This yeah, there we go.
Okay, thanks.
Thank you.
That's fine. Hi. Hopefully everybody can see that.
Yes.
Great. Right, so I'm going to just give a brief overview of the group. I mean, you've already heard from Wei about the CCP and some of the activities we're doing there around the nuclear. So this is a little bit broader around the department and some of the other work going on. So we're part of a department known as Computational Science and Engineering Division within the Scientific Computing Department. And within ours, we have four branches. We look after the engineering, but we also have physics, biology, and chemistry. All of these have a long history in CCP activity from different areas, but it gives a kind of indication of the range of length scales that we cover, from electronic structure of matter looked at in the computational physics, lots of computational biology work that Wei has mentioned with BBSRC and MRC, and a very strong computational chemistry activity as well, which has included looking at materials for nuclear storage and looking at damage to nuclear vessels using molecular dynamics. We've just started a little in-house project, as a short project with us, using molecular dynamics to investigate some of the properties of molten salt reactors, to try and understand some of the terms in there. The research topics that we cover are quite wide-ranging over the years. Some of these are active at the moment, some are a bit quieter, but everything through turbulence, combustion, free surface flows, aerodynamics, environmental flow modeling, micro and nanofluidics, rarefied gases, energy. Of particular interest at the moment that we're looking at is the Petra and exascale software development. We have a number of projects around that. And in multi-physics and multi-scale simulation, which includes quite a bit on coupling, which is one of the big challenges to overcome. So this is just one example of some of the activities going on. So the blood pump that you can see was an FDA challenge, looking at how they could look at the hemocrit in the blood as the blood leaves the pump. We have
Steve, I think your presentation is, you can just full screen your presentation. So
it's on full screen with mine.
Now it only shows the first page.
Oh. Okay, I have no idea why that is. It's showing us full screen on mine.
Okay, it's maybe you have dual monitor.
Yeah, I can unplug the other monitor to see if that causes an issue. So, can you see the second one?
Yeah, that's yeah, I think that's
okay. That's never happened before. Okay. Well, okay, just very quickly, that's just showing the various different activities. It's actually not showing very well on my screen now, which is interesting. I can only see a bit of my slide, but you can see all of it.
Yeah, we can show your current slide and your next one with.
Okay. What I'm going to do is just end it and start again, because I think it's got screwed up in a classic Windows way.
Okay.
So, can you see it now?
Yeah, that's the first page, yeah.
Yeah, no,
yeah,
fine. Yeah.
Great. I don't know what happened there. It's never done that before in all the times I've used it. So anyway, okay, so this is briefly going over again, just showing the length and time scales that we're operating over from electronic structure right the way through to the macro scale and the various sections. These are the research topics that we're looking at. I've already run through them, but the main thing to focus on are the ones in red, which are the areas that we're working on quite extensively at the moment, which is on the Petra and exascale and the multi-physics and multi-scale. And this is just some of the examples of what we're doing of projects. So at the bottom right is part of an EPSRC project that we had looking at molten salt fast reactor. The top right is looking at coupling. And in the coupling, we've been developing the mil-scale user interface, which is a collaboration with Brown University in the US. And this is an open source package for coupling, which is based around the MPI directive. So it's very portable and easy to add to codes. There's still a lot of work to do on developing that coupling, but our intention is to use this coupling so we can use the best code that we want for doing a particular application and then target that and couple them together. Given time is now a bit tight, I'll move on. The top left one is a mass spectrometer that we were working with, which was a former project that we worked on. And so been some talk about sort of fluid structure interaction, which is a project that just happened. So sample projects, we have a program grant that's currently running. This is looking at more nanoscale and microscale activities with Edinburgh and Warwick. There are 3 high-end computing consortia which are quite relevant to what we're doing here. There's the UK Turbulence Consortium. We get a lot of our compute time within the consortium from UKTC. There's another one on turbulent reacting flows, and there's another one looking at mesoscale modeling. And highlighted in red is the next machine, which is Archer 2, and I'll just briefly touch on that on the next slide, just to say what we're targeting. There are 3 CCPs of relevance at the moment. There's the nuclear thermal hydraulics, as we're at the meeting today. There's also a CCP in turbulence. It's looking at fundamental DNS. And there's a CCP in wave structure interaction. And part of the target there is to look at large-scale FSI type of projects. In terms of exascale, we are nowhere near as active in the UK as they are in the US. So we do have one called Excalibur, which is looking at trying to coordinate the activities. And there's a couple that are currently running, which is looking at turbulence, and one looking at mesoscale modeling. And one of our team, Alex Gullen and Charles Moulinek, have just had a project funded now on looking at fluid structure interaction framework for exascale. So the machine that we've just had installed, although there's only 4 cabinets at the moment, the rest is sort of on its way. It's a Cray supercomputer with 5,800 compute nodes. Each of these have the AMD EPYC Rome CPU. So just under 750,000 cores in total. The peak, but the peak performance is 28 petaflops, and based on the June ranking from 2,500, top 500, assuming we've got 50% of the peak, we'd be around about 14 petaflops, which would put Archer 2 in the top 20 of the machines, somewhere around about number 15 or 16, I anticipate. And we're already planning to have a substantial activity on Archer 2. So that's it. Sorry for overrunning slightly with the mess up on the screen.
Yeah, thank you, Dave.
Let me just stop sharing.
The next one is Shuisheng from University of Sheffield.
Okay, right. Let me find the right screen to share. Is it?
Yeah.
Okay, excellent. Right. Okay. So at University of Sheffield, nuclear research mostly includes research on advanced nuclear materials and waste management. And this is largely within the Department of Materials Science and Engineering. And then in the Department of Chemical and Biological Engineering, they are working on spent fuel reprocessing. And here at in the Department of Mechanical Engineering, we focus on thermal hydraulics, which is something I'm going to talk about. But before that, obviously, I need to mention nuclear AMRC, which is focusing on manufacturing. And now, in terms of nuclear thermal hydraulics, we focus on 3 things. And the first one is very much like a general modeling to support the design of advanced generation 4 reactor systems, and also to support the safety case design modifications and operation of AGRs. And following that, we also work on the general computational tools and methodology development, including both high fidelity simulations and coarse grid CFD. And finally, number 3, we're working on some fundamental research on natural circulation and transient projects. So next, I just gave you just some examples of research projects currently happening within the research group in the department. Now, the first one is on the modeling of advanced nuclear reactor designs. We're involved in 3 types of reactors. That's liquid metal fast reactors, and SCWR, supercritical water-cooled reactors, and more recently on high-temperature gas-cooled reactor. And within the first group, we're involved in the base digital reactor design Thermo Hydraulics, led by Fraser Nash, consultant. And here we been working on aerosol dynamics in the cover gas region in liquid metal fast reactor. And more recently, we focused on heat transfer to liquid metal in complex geometries. And that will be discussed later on by Shuisheng. And in the framework of EPSRC and DOE project, we are working together with STFC and Edf Energy on the safety model development and validation in the area of liquid metal fast reactor to support the activities in instrumentation technology development in the US. And in terms of the second topic, SCWR, we've been working on this for quite a while now, over 10 years. And those were supported by mostly EPSRC project, but also IAEA CRPs. Now, more recently, we are involved in EU projects. So in all those projects, we look at the physics and modeling, and this is also some of the bases which lead to the development of numerical methods, which I'll talk on the next slide. And the last one is on the HTGR. Again, this is part of the EPSRC DOE, collaborating with a different group of US colleagues. And again, on the UK side, it's from STFC and EDF. Now, in the AGRs, so we've been working in like fuel route modeling. There are a couple of PhD scholarships which enable us to develop something quite interesting. And then in terms of the core reactor core heat transfer, is something I started with. So we've been probably working with that group for over 10 years. Then the last one, we talk about safety case. This particular one is a recent safety case which we have done a bit of work to support this in area of 3D thermal modeling. But in the past, we supported various safety case development. Now, in the area of computational tools and methodology development, as a group, we have developed a number of safety software codes, and probably that's what we want to do. But that also includes Chapsim for DNS, and obviously the main developers are Mehdi Seddighi, who is currently at Liverpool University, and also Dr. Wei Wang, currently at STFC. And in the second item, we actually developed a 3D porous medium model called Freedom for AGR field bundles. And this is something we hope to use to support all the safety cases related to natural circulation, both in terms of intact fuel and dropped fuel scenarios. And the third item on this is a development of a novel sub-channel CFD modeling methodology. This is funded by Base Digital Reactor Thermo Hydraulics, again led by Fraser Nash. And again, this will be discussed by Dr. Bo Liu in the afternoon. And lastly, we participate in this CCP, hopefully to support and benefit from the development of CHAPSIM and robust CFD. And what is this? This is natural circulation and transient flow research, which are relevant to various kind of scenarios in nuclear sector, both in terms of the transient flow startup or shutdown, but also in terms of passive cooling, buoyancy-driven flow. I think that's everything.
Yeah, thank you, Shuisheng. The next one is Hector from University of Manchester.
Okay. Okay, can everyone see the full screen?
Yes.
Okay, hello again. Over the next few minutes, I'll try and give an overview of some of the current and also recently completed research in the area of thermal hydraulics within our group. Down here, I have the names of the academics and PDRAs that currently work in this area within the group. I should perhaps also add that at Manchester, we also have the Modeling and Simulation Center set up by Edf Energy and now being joined by other external collaborators. We also have the Dalton Nuclear Institute, which provides and supports nuclear research right across the different disciplines. And also in common with, jointly with Imperial College, we are a Rolls-Royce nuclear nuclear research center. Here, I'll just quickly go through some of this list of items. It is actually by no means exhaustive. I just realized, for example, that I left some of the experimental research that my colleague Andrea Chioccolini has underway on boiling, but it will give you a flavor of what we are up to. Passive cooling loops is an area we are quite active. We have funding from BASE through the BASE Friends and Arch project, which Dr. Wilson will be discussing further later on. We also have another PhD studentship co-funded by Edf and the University of Manchester, who will look at more fundamental aspects, starting with more fundamental natural convection flows, where the student introduced the analytical wall function into Code Saturn, which, as you can see here, it has quite a big impact on the accuracy. And he's also now looking at some of these natural convection loops, and in particular, focusing on the transients and how that can be improved by including conjugate heat transfer and also the characteristics of the heater. Another area that we started working a lot recently is liquid metals and molten salt research. Funding is mainly provided by the joint EPSRC and EUP grant jointly with the University of Pittsburgh. Here are some examples of some of the initial work we're doing to provide some information to our Pittsburgh colleagues on how to design a molten lead corrosion experimental rig. Then we'll go on to produce some high fidelity simulations of this in order to compare with their experimental data. In parallel to that, we also have 2 PhD studies looking at fundamental aspects of low Prandtl and high Prandtl number heat transfer. And later on in 2021, we will start another project funded by Westinghouse through the BASE AMR competition on modern, on liquid lead heat transfer as well. Another area is that of conjugate heat transfer. We recently completed, had a PhD study completed in which we've been looking at the generation of thermal fluctuations due to turbulence within the flow and how they propagate into solid walls. Initially looking at simple channel flows and comparing with DNS data. Having developed the model, more recently, we applied that to these more complex 3D case for which there is also DNS data. And as you can see here, it seems to be providing pretty close agreement with the DNS. More recently, we started another PhD study looking at transient conjugate heat transfer through pipe bends. Another area is other fluid structural interactions. What I show here is from an earlier PhD study that has been completed. We now have another experimental PhD study co-funded by Edf and the University of Manchester. And in parallel to that, we have another 2 PhD studies looking into developing CFD modeling for these cases where we have flow-induced vibrations when the flow is parallel to the rod, which is relevant to PWR fuel passages. Another area that we started recently as part of our collaboration with Rolls-Royce is liquid injection into vapor, which is relevant to the pressurizers in PWRs. We have an experimental PhD investigation, and this is the rig we developed and some of the initial videos that images that we produce for these injections. That is funded jointly by Dalton and Rolls-Royce. And we also have another PhD studentship from the Green CDT, again co-funded by EPSSC and Rolls-Royce, looking to develop CFD models for these cases and use experiments for validation. Another area that we recently completed is that of turbulent flow through porous media. We had one PhD study that looked at, collected a lot of experimental data for flow and heat transfer through passages which include metallic porous foams to enhance heat transfer. Here are some of the PIV data that we collected. And in parallel to that, we had another PhD study looking at the turbulence modeling of such flows, and especially at improving and developing models that handle the turbulence around the interface between the fluid and the porous regions. And I suspect that's my last one. So hopefully I managed to give you a quick overview within the time, within a reasonable time. Clearly, there is a lot more to be said about those, but that's perhaps for another day. Thank you.
Thank you, Hector. The next one is Christos from Imperial College, London.
Hey, hi, so it says I can't share the screen. Let me try again. Okay. Does that look okay now?
I think you need
okay?
Yeah.
Now it's okay. Yeah.
Okay. Thanks very much. I think we had a presentation which mentioned the work in the Department of Mechanical Engineering, the first one, and also some mention of other colleagues in other departments. So I'm going to focus on the Department of Chemical Engineering. There were three main academics in our department working in related areas. Unfortunately, Jeff Hewitt passed away, so it's really down to myself and a colleague of mine called Marcos Milan. In our group, we have this is the size of the group, and we tend to do work that goes from all the way from sort of processes, and I mean sort of heat transfer, mass transfer processes, up to technologies, devices, and systems. And I won't really talk to you about everything, but I'm going to focus basically on the red bit for this particular presentation. Being experimentalists, I suspect that the most useful thing we could do for people who are on the call today is provide high quality experimental data for model development and validation. So I'm going to be focusing on the work we've done on the sort of bottom two, the bottom half of this slide. Okay, so we in our department, and I'm speaking also here on behalf of my colleague, we've done some work a few years back starting from fluoride salt cooled, and also we developed an interest generally in sort of molten salts as heat transfer fluids for nuclear applications and nuclear reactors. This was an interest of Jeff Hewitt's, and we had a number of, a couple of PhD students that were funded through the CNE, the Center for Nuclear Energy at Imperial College. But I think really the core of what I'm going to speak about today is the second bullet point. Although I will say a few things about the first one. I'm basically going to present to you some experimental capabilities which we're quite keen to apply to flows which are of relevance, I guess, for model development. We do then a lot of work on, let's say, what happens to the heat recovery, utilization, power cycles, and sort of whole system analysis. It's out of scope of the discussion, but I think it's useful that the people on the call know that, you know, there are some people that sort of trying to include the role of nuclear energy in the UK in a more sort of high energy system modeling sense. So I'll go quite quickly through a number of slides. I mentioned we do have an interest that we did and we still do in molten salts as heat transfer fluids and the design of different types of reactors. You're seeing here some work we did on pebble bed reactors with salt as a heat transfer fluid. We very quickly discovered that you know, when you're doing CFD, you're just entering thermophysical property values, which is a little bit of a black magic. So there was a lot of work, a whole PhD went into measuring thermophysical properties of molten salts outside of the ranges where actually data can be found in the literature. We then went up to the level of, you know, considering the reactor and power cycle and the whole plant. So trying to optimize the plant, there's an interest there, and trying to design a drag system, which is basically a passive cooling system for these types of, and other types of reactors. And we found some interesting results. This is published data on how in some cases you can have freezing of the salts in these types of heat exchangers, which is basically a very bad news if you're trying to design something which is passively safe. Okay, so let's go into the sort of the main thrust, I guess, which would be of interest to the people here. In my group, we specialize a lot on interfacial flows, two-phase flows, typically gas-liquid or liquid-liquid, where there's a, you know, where the two liquid phases are immiscible, also solid-liquid, solid-gas. Most of the things I'll show are liquid-gas, but there are other types of flows, and we do a very wide range of measurements. Here you can see moving frame of reference measurements on the left-hand side in relatively well for a lab scale, large scale sort of experimental facilities. So we're talking about up to 40, 50 millimeters and 7 to 8 meter length. So, you know, not small scale, not bench scale. And the idea here is basically to find out where the interface is and to provide velocity field information. If you have a two-phase, here I'm showing the example of a liquid gas system, optical measurements which are required to perform things like PIV in single-phase flows become much more difficult because of course you have distortions wherever you have the interface, you have reflections, you have refraction of light and so on. We've spent a good 10 years, 12 years since I joined the department, basically developing techniques that allow you to do measurements in these types of flows and to measure velocities, etc., and interfacial locations, which gives you a sort of phase distribution with different techniques. And here I'm just showing one particular case where we're trying to measure or identify the free surface of a film, where you can see that the true surface of the film is actually hard to get. So we have techniques which allow you to find the real location of the film. Everything else above this red line, I don't know if you can see my cursor, but basically this is called the false interface. There's no real liquid phase over here. The liquid phase is only below the red line. I think really the main point here is that when you're trying to do measurements in two-phase flows and in boiling flows, which I'm going to get to in a second, you need very dedicated experimental techniques, and we've been trying to develop this for a number of years. So here's us basically going from just identifying interfaces and velocities to now starting to do temperature measurements, and you'll have all sorts of techniques that allow you to do that, either based on laser methods, so fluorescence, which is temperature dependent, or infrared measurement techniques, which we've been applying to different types of flows. Here we have a film which we're trying to measure heat transfer coefficients in. And I guess the interesting thing here for people who are on the call is the sort of space and time resolved nature of these measurements, right? So we can get a spatial distributed measurement of a heat transfer coefficient over some surface and time resolved. And then effectively then taking these types of techniques and trying to look at a much more complicated flow. So this is boiling, right? So pool boiling, and this collaboration with Matteo Bucci at MIT. So this is actually work that was done at MIT in the nuclear department there, with some of the work in terms of applying techniques that sort of we brought. And I'm going to show a few sort of typical, the type of information really that we're trying to get to with these measurements. So you see here, you see on the top, a bubble which grows and detaches from a surface. So you can see there that the wall temperature underneath the bubble is lower. Below that, you see the velocity field around the bubble as this rises. So this is from a different camera angle, right? So the top image is looking down on the heated surface where the bubble rises and then detaches, and the one below it is looking at the flow field from the bottom, sorry, from the side. And on the right-hand side, you can see the temperature field around the bubble as this lifts off the surface. So this is to see things like temperature boundary layers and other sorts of effects behind the bubble as it rises. Okay, so I think that really summarizes what we've been trying to do and what are our next steps. We're trying to go, as I said, most of our experiments are sort of large-scale experiments. We're trying to go not just in terms of the size of the channel, but also potentially the measurement domain towards smaller domains. So we've got a microscopy system that we're building up at the moment, and we have also an EPSRC funded grant on small channels that we want to kind of start applying these techniques to, and we're sticking with boiling. So we're talking about two-phase flows. We also have an interest, we have a Marie Curie fellow who's arriving in October, November, in doing measurements in basically in CO2 at supercritical conditions with heat transfer. And then you have buoyancy effects and a lot of difficulties, again, making measurements. We want to look at, this is basically work that Matteo does at MIT on surface engineering, nanoengineering, and to what extent you can affect things like the heat transfer performance, let's say at a very high level, through these types of modifying surfaces. But also personally, I have an interest in the interface. So, whether through particles or other types of... yes.
Sorry, I have to interrupt you.
I'm done. This is my last slide. Okay, I think I'll finish it there. I'm done. Thank you very much.
Thank you. The next one is Mehdi from Liverpool John Moore University.
Right, let me see if I could share my screen. Is it all right? Can you see it?
Yes.
All right, brilliant. Thank you, Wei. And I think it's time to say good afternoon, I think. So good afternoon, everyone. And yeah, I'm going to briefly talk about just a very short summary of what we are doing and related to, thermal hydraulics. Is mainly some recent and current fundamental research that we are doing. And part of the work has been done when I was working with Shuisheng in Sheffield. I'm working with him in some project and some others with other collaborators. There are obviously a couple of researchers who are helping and doing research on this mainly. And yeah, the first topic is on the turbulence when we have non-periodic flow. So we have one turbulent state, and at some point we accelerate, decelerate to another turbulent state, and there is a time following that acceleration or deceleration chain that we call it transient period. And during that period, the flow would change to reach to the new turbulent stage. We have done research on smooth surface and rough surface for this, type of flow. And for the case of smooth surface, there is, although despite the initial state is turbulent, the flow has shown a laminar to turbulent transition, a process which resembles what we see in the bypass transition. There's lots of details on that. We have shown that 3 states of pre-transition, transition, and turbulence states have been shown by the flow following that acceleration. Again, this is despite the fact that the initial stage of the flow is turbulent. So we did also the research on when we have rough surface, and the roughness is modeled using a simplistic pyramid roughness. And again, the initial flow state was turbulent, although at quite low in terms of the roughness definition, that is at low, near the hydraulically smooth region, and then we accelerated the flow to nearly fully rough regime. And again, in terms of procedure, we can see that is, similar behavior have been shown for the development of turbulence, and which resembles again roughness induced transition. So in addition to that, because all of the things are for turbulence, on-state turbulence, when we have accelerating, decelerating individually. And obviously we have done that for some other flow condition, that it is not only towards the fully rough regime. Within the transitional rough regime, there are also some research we have done on. And the other, type of research on study that we have just started together with STFC, Charles Mulinek, is to look at, pulsating flow. Again, in pulsating flow, there are lots of literatures already, but this is, some contradicting sort of things presented in terms of how pulsatile flow, affects the heat transfer as well as flow only cases. In some cases, they showed enhanced heat transfer. In some cases, it's suppressing the heat transfer. So we are looking at that to understand detailed flow structure and flow and heat transfer performance when we have pulsatile flow. In terms of the computational and the code development part, we also look at some modification to ChapSim that I'm sure you're already probably aware, a few times by Wei and Shuisheng, that for parallelization, Wei has already started that. And some other aspects of the code development that we are going to contribute to is to look at, to improve the spatial discretization error. And also we got, quite many post-processing subroutines, as Wei mentioned earlier, developed by different users, but we are going to combine them and make them in one subroutine. In particular, the main focus is to look at the unsteady flow. And when I say unsteady, I mean changing mean flow, not instantaneous, which is obviously changing. Again, in terms of drag reduction, in some studies shown this is for some particular amplitude and period, we see some drag reduction. But again, this is something that we're going to look at. And yeah, the other type of research that we are doing is to look at some drag reduction using superhydrophobic surface. This is a research that we are currently doing and just getting some biomimetic Texas surface using that Baksume, and we got some quite interesting and promising results. This is a simplistic model for that Baksume. And we got quite, significant drag reduction. And Yeah, in terms of the methodology, I think I don't need maybe to explain that much. Wei has already indicated that we use ChapSim, and is now for more than a decade that is under development by different people, and we are also aiming to improve it, more and more over this CCP project, as well as this EPSRC project that is working on the Pulsating Flow. Thank you very much. I probably wants to stop now.
Thank you, Mehdi. Our next presentation is by Eugene from University of Cambridge.
Hi, everybody.
So let me see how I could stop share.
Okay, can everyone see this? Okay, so this is an overview of Cambridge University Engineering Department activities. I should say that this is not a reflection of what the university as a whole is doing. There are various bits, pockets of activities in other areas like materials, policy and economics and so forth. So in engineering, we are pretty much only 2 full-time academics with 2-3 affiliated faculty, and at any given point in time, we're between 10 and 20 PhDs and postdocs. We've graduated quite a few recently, so we're in the bottom of the cycle at the moment, and hiring. Another thing to mention is nuclear energy master's course that is run out of engineering, which I'm directing, and that's a lot of master's level dissertations to supervise. So in terms of research areas, we're more of a practitioners of thermal hydraulics models, aiming at the design of nuclear energy systems, and the emphasis here is on systems because it requires not just thermal hydraulics but other things. My colleague Jeff Parks is well known in design optimization methods, which can be applied to nuclear but also other applications. And engineering department also, as many of you may know, have academics who are not actively involved in nuclear, but with a wide range of knowledge and expertise in thermal fluids, like Peter Davidson and our fluids network, Matthew Juniper, who was the leader. I don't know whether he still is, and a few others. So these are the areas of activities, and I will just briefly mention a couple of recently completed PhD projects to give you a flavor of what we've been doing. So one project is on BWRs with superheater. Some of you may remember this Ferry Wisono, who was a PhD student in the group, participated in nuclear thermohydraulics interest group live meeting a couple of years ago. So he presented some of his work. So the idea is to attach a superheater to a BWR, which allows improving many design characteristics of such a system. So it can be smaller, it can improve thermal efficiency of the whole thing, and load follow and so forth. So this required a range of coupled tools that has also have to run sufficiently fast to allow sort of full system optimization. So so thermodynamics of power cycles coupled to various effects that it will have on the nuclear reactor system, which through this external superheater can run at 100% power 100% of the time, and load following is enabled by this variable heat superheater that can draw its energy either from burning natural gas or hydrogen or ammonia, or using heat stored from things like concentrated solar, for example. Another recently completed project is that required several sort of different angles of expertise is a molten salt reactor, more in particular Moltex version of it. Some of you may be familiar. So this is a concept that uses molten salt as a coolant, which is encased in relatively thick fat fuel pins, and the clean salt as a coolant, which removes the heat. So the trade-off that we were trying to evaluate was, so some of you may know that Moltex is designed as a burner reactor. We're trying to see whether it can be a breeder reactor. So we want to try to breed actinides and improve fuel utilization. So it was apparent from the beginning that it should come at some cost of achievable power density, which is the main driver of economics of the reactor. So this breeding potential versus power density was a very interesting exercise, which required a wide range of models to work together through coupled interfaces. So well, one of the more interesting things were development of heat transfer model for this naturally circulating heat generating fluid within a pin, which is then that heat is removed by we figured a downwards flow of the coolant is beneficial because that enhances the circulation and allows greater heat transfer, so lower the fuel temperature, fuel salt temperature, and as a result allowing higher power density. Another exercise which was recently completed is a project done for NNL as part of their collaboration with the European project on space reactors. So this is another sort of multi-physics exercise that required both nuclear and fluids, thermo hydraulics, and power cycle models all working together within reasonable time, and to be fed into a genetic algorithm optimization for evaluating minimal mass, which is obviously critical for space reactors. The main question was, all space reactors used to use highly enriched uranium in their cores, which is politically problematic, and we wanted to see what will be the mass penalty if we switch to low enriched uranium. So it will be heavier, but we didn't know by how much. So by having a pretty detailed model of power cycle and heat exchangers and the radiators and so forth, so coupled multi-physics models allow that optimization to happen. So we came up with a reasonable answer. I will be happy to expand on any of those, and thank you very much for your attention.
Thank you, Eugene. The next talk is from Chris Harrington from UKAEA.
Thank you, Wei. Just share my screen. Let me know if you can't see that.
Yes.
Okay, thanks everyone. So my name is Chris Harrington from UKAEA. This talk is a bit of an overview. It's quite broad and not too detailed on our interests at UKAEA. Our mission is to realize fusion power, but to, in doing so, explore enabling technologies, of which thermal hydraulics is obviously a big one. So there's strong overlaps with fission, but also some quite unique challenges as well. So I'm going to start just by going through the basics of a fusion reactor. A lot of you probably already know a lot of this, but I don't like to presume, so it's always good. This is taking the EU demo project as an example. Effectively, we have a torus-shaped machine, of which you can see a segment here, a burning plasma in the center confined by strong magnetic fields. And around the wall of the machine in this gray area, divided up into blocks, is a component we call the blanket. That absorbs neutrons. In doing so, it becomes hot, and the challenge is to extract the heat from that blanket, turn that heat into steam or some other fluid to drive a turbine, and use that to generate electricity. So that's the internals of the machine, but that obviously has to be supported by a large range of other systems outside the vessel. This is showing one particular design for a water-cooled reactor where we would have this quite large and quite complex ring header system with various piping channels coming down from that and eventually connecting into the upper port of this machine. And around the outside, you can see standard components that you'd recognize on a fission reactor, such as a U-tube steam generator, pressurizers, and so on. The blanket components themselves, these gray blocks that we're looking at on the left, might look something like this. This particular one, again, is water cooled. It's effectively a steel box full of molten liquid metal. It's a lithium lead eutectic. That liquid metal is circulating slowly and getting hot. So in order to extract the heat, there's a network of pipes, U-tube shaped pipes, running horizontally through that. And through there, we are running liquid water, pressurized water, at sort of PWR conditions to extract the heat. So you can see sort of the scale of the problem is everything from this very large circuitry up at the top, which then breaks down into various branches all the way through into smaller channels to extract the heat from a breeder blanket component. And within that, you've got liquid metal heating up in a strong magnetic field. So there's MHD effects. You've got heat transfer from the metal to the pipe wall to the water. So you've got all of these very complex problems, plus you've got neutron bombardment and a non-uniform heat distribution through the axis of this component. So the question we're trying to get to the bottom of it is, how on earth do we simulate, test, validate a power plant that looks like this? So in terms of our aims at UKAEA, what we're looking to do is develop the capability in both simulation and testing of components for virtual engineering and the operation of some of our facilities. The big one that I'll come on to in a bit is called Chimera. And we want to do this collaborating extensively with other parties, universities, industry groups, and so on. We're aware that there's a lot of excellent expertise out there amongst a lot of the people on this call. So really we want to work with others where we can, and hopefully the CCP is a prime opportunity to do that. In terms of particular needs, we need to bridge the gap with plant level simulations. So that's what I'm talking about when I talk about that larger loop, but also breaking down the simulations into more detailed simulations of the blanket. We need to be able to explore different designs of components, often with challenging geometries. So that water-cooled blanket that I showed you is just one design. There could be many others involving fuel pin type arrangements or pebble beds. And then even within that, there's optimization to be done in terms of geometries, sizes, and so on. We need to be able to do all of that design work, and we also need to verify the performance of existing designs. So that involves putting them under test conditions where we can. A lot of the methods that we have at the moment at UKAEA, we have a reasonable base in thermal hydraulics. It tends to be a little bit in pockets around the organization, and we tend to use either system codes or quite industry standard CFD tools such as ANSYS, Fluent. A lot of these are okay, but really we need to take that to the next level. And that's what we're aiming to do over the next few years. Our priority areas are listed here on the left. So that involves a robust and high fidelity CFD, where I've pinched those words from the CCP because it very much is about that. But specifically that we need to be looking at water, liquid metals, potentially molten salts, supercritical fluids, so the whole range of possible fluids that could realize a fusion reactor. We need to exploit high performance computing and parameterized workflows so that we can come up with designs of different in-vessel components, but also tweak those designs and optimize them as far as possible to improve the heat transfer. We need to be able to capture complex phenomena, so that might include natural or at least mixed convection, conjugate heat transfer, and high and low Prandtl number flows, particularly relating to molten salts or liquid metal usage, which might be very enabling for a fusion power plant. And that last point there is about linking all of these things together. So MHD effects, if we're talking about liquid metals in magnetic fields, neutronic simulations, and going from the system code to the CFD level where we need to if we want to simulate the entire plant. Some particular projects listed there on the right. So prediction and verification of components in Chimera. This is a facility I'll talk to you about in just a second. It's for applying blanket type components to expected loads so that we can characterize the performance. We need to be able to do component design on different fusion power station projects. So demo is the one example we looked at the start. It's a European project. STEP is our own UK-based project looking at a slightly different version of reactor. But again, we need to do rapid design components that we optimize for those two. In the meantime, we're also progressing the National Thermal Hydraulic Facility, which is something we can possibly talk about a little bit later. That's really, we're acting as overseers of a design of that project so that we can cost it up. And the last point here is not particularly project related, but one of the main things we want to do is link all the codes that we use for doing a lot of this analysis for fusion to the same codes in fission in order to get a sort of unified capability where possible. So that's enough words on slides. We are opening a new centre, which hopefully a lot of you are aware of already in Yorkshire, just outside Sheffield. And this is going to house a lot of our experimental capability. It's on the Advanced Manufacturing Park, just between Sheffield and Yorkshire to be precise. We've got a plot of land here. The building is progressing very well. So this was it earlier this year, and this is it taken just a couple of weeks ago. So this facility will be open by October, and main bits of kit coming in beginning of next year. The idea of this facility, we're looking to house a new thermal hydraulic group up there. So that will bring together a lot of our capability that we have at the moment under one roof. And in particular, this building will host our Chimera experiment, which, as I say, is for taking a component scale blanket module and applying heat loads, magnetic fields to that module with instrumentation so that we can both simulate and characterize its performance and validate that performance. So here's a quick little mock-up of how that will look. It is... Sorry,
Chris, time runs out.
Okay, this is my last slide, so I'll just skip through this quickly. There's a blanket module in this central position, and around that there are magnets supplying high magnetic fields, and there's cooling coming in at the top, and there's a heat load being applied to the front of this. So these are all magnets and a vacuum vessel that houses it. It's about 1 meter in scale. So this is a serious piece of engineering, high heat loads, high magnetic fields, high pressure water, high temperatures that we'll be able to simulate in this facility. And we're looking for ways to characterize that flow and validate it against our models as well. So that's quite an exciting time. And I'll just leave a sort of virtual business card there on the screen. Any questions, just feel free to email me.
Okay, yeah. Thank you, Chris. The next one is from Ehimen Iyamabo, or Edf Energy, R&D UK Center.
Hello everyone, good afternoon. Can you see my screen? Very well.
Yes.
Okay. My name is Ehimen Iyamabo of Edf R&D in UK Center. And I'm also a concluding PhD student at the University of Manchester. I'm here to give a brief overview of what we do at the Modern Simulation Center at the University of Manchester. So, R&D figures. We have about close to 2,000 employees in 2,000 employees in France and about 225 employees outside France. 13 laboratory labs and set up all over the world with about 29 nationalities represented and 117 PhD students either been funded or supported by us. And we currently have a budget of about 510 million euros, with about 2/3 going to supporting the business activities of the group and 1/3 for forecasting or paving new technologies or new systems in our group. We have a very good supercomputing facility with a capacity of about 4 petaflops. So the R&D group has centers all over the world with we're scattered in France, Germany, Italy, United Kingdom. In the United Kingdom, we have centers in London, Brighton, and Bangor, and as I've already mentioned, the Modern Simulation Center, which is embedded in the University of Manchester. And so this is an overview of the R&D staffing in UK Center in UK. So overall, there are about 70 full-time researchers with 10 based in Manchester. We support 40 PhD students overall, with 8 being supervised currently at Manchester, and we're quite diverse with about 15 nationalities. 100% of our funding is from conventional contracts to the EDF business units, of which 26% comes from corporate activities and 10% from public funding. So activities in the modeling and simulation team. So we are in the Modeling Simulation Center at the University of Manchester. We are focused on developing high-end numerical skills in mechanical, structural, and nuclear engineering to tackle the numerous challenges in thermal hydraulics and solid mechanics stress in the nuclear industry. It involves particularly a lot of software development, of which I'm sure you're aware of the numerous suites that we have, the numerous open source codes that we have at EDF, benchmarking and the development of state-of-the-art industrial models and publications in 3 key areas, which are solid mechanics, structural integrity, computational fluid dynamics, and now we are increasing activities in data analytics and artificial intelligence. So in structural and integrity activities, our research focuses a lot on the following things you see on the screen, which is the studying of material aging of our AGRs, fracture mechanics and world model, which we have strong collaboration with at the University of Manchester, damage mechanics and seismic behavior, materials and graphite cracking, and also we do have activities in civil engineering. In the computational fluid dynamics, we focus a lot on finite volumes, of which we have developed a number of suites, particularly called Saturn and other open source codes. We have research in free surface. We're currently expanding our research in measurement methods, which is quite relevant to us, particularly with the SPH. At the Modeling Simulation Center, we have developed a lot of advanced stability models, and particularly in RANS and recently for hybrid RANS LS methods. And now we're also we also have research into multi-phase and condensation activities. So recently, so our research activities in both CFD and instructional side generate a lot of data, data from our models, our experiments, and our different investigations. And now the team is now focusing on developing state-of-the-art techniques in analyzing this data and transforming this data into more valuable information to enable us to make more effective decisions in the future. And our data analytics involves data assimilation, uncertainty quantification, model reduction, and machine learning. So the Modeling Simulation Center and the R&D group in UK has a lot of engineers with a very varied skill sets. which is used to support a wide range of activities in nuclear generation and waste and decommissioning, in developing technologies in renewable energies, and also developing smart solutions or innovative innovations in smart cities and enhanced visualization. So I'll move on to our partnership. So our Modern Simulation Center is split into two sides. We have the University of Manchester side and the EDF side. And University of Manchester side is supported by the experts or staff members from the academic team at the University of Manchester, who are in charge of the supervision and supervision of PhD's research and also proposals. And in the EDF side, we have about 10 permanent staff of researchers and experts, and we support also a lot of interns and young engineers, and we develop them, we upskill them. So we're active in the development of new generation of scientists and engineers. And with Manchester and EDF, we find a right balance between advanced research and also industrial delivery. Also, we also collaborate with a number of industrial partners, including NNL and Wood. As earlier mentioned, we are based in University of Manchester, which enables us to basically pick up a number of enjoy being close to a lot of actions in research in different departments in Modular Simulation Center, which is the home in Joshua, which is the home of turbulence modeling and the Modular Simulation Center, in the process of which housing.
I think your time runs out.
Oh, okay. All right. Okay. I'll just end here, and I think this is my last slide. So thank you very much.
Thank you. Thank you very much.
All right.
Our next talk is from Mac Rabbit, Edf Energy Engineering.
Hello all. So I work for EDF. Can you hear me?
Yes.
You're good. So I work for EDF. We operate the commercial nuclear reactors in the UK. So we have 14 gas-cooled reactors and 1 pressurized water reactor. That won't be the case for too much longer. The 2 reactors at Hunterston will stop operating early in 2022, which is just over 1 year from now. And they are stopping due to the challenge of making a safety case from cracks in the graphite core. Our 2 newest gas-cooled reactors, which started operating in the late 80s, so that shows you how long ago it was, they'll be closed in 2030, so that's 10 years from now. So in 2030, we won't have any more gas-cooled reactors operating. We are currently building a new pressurized water reactor at Hinkley Point C, and that will start operating in 2025. So the ratio of gas-cooled reactors to pressurized water reactors at the moment, now we're considering that Hinkley is an operating reactor, is 14 out of 16. So most of our thermal hydraulics support is done on the gas-cooled reactors. So in the period of time between now and 2030, we've got to move from supporting a fleet of ostensibly gas-cooled reactors to a fleet of pressurized water reactors. And we're hoping to build another PWR down in Sizewell as well at some point in the future. So I'm showing you a slide here of where we are at the moment. So thermal hydraulics in 2020. So we have a thermal hydraulics group, and we support the operation of our nuclear reactors in 4 main areas. So we have a team which looks at primary circuit analysis, which looks at what happens in the primary circuit ostensibly during normal operation, steady state, and also postulated faults. And that uses a network flow solver called MACE. The next team looks at management of boilers, and Ehimen, the previous presenter, is working on building a CFD model of a boiler, by the way. But this team looks at managing boiler tube temperatures to make sure that we can operate to the end of the life that we'd like them to operate to. We also do things like thermodynamic cycles to make sure we can get the most of our reactors, reactor control. So they use codes which are, again, of the network flow type of technology. The third team is core thermal hydraulics, PWR, core thermal hydraulics, which looks at the thermal hydraulics in the core. And our fourth team, which is what I'm part of, looks at detailed analysis. So quite often we'd like to know quite detailed temperature distributions. And we would use CFD, for example, to do that for us. So in the thermal hydraulics group at the moment, we've got 14 people working. As well as that, we have another group of thermal hydrolysis working in safety studies group, which is essentially looking at what goes on in a PWR. I think there's maybe 5 people looking at that. So that's what's going on in at the moment. And in 2025, which is just 5 years' time, we're going to have to move to much more support of the PWR stations. We're going to have to carry on supporting the AGRs, but we're going to have to learn how to support the PWRs. So we haven't yet decided precisely which tools we're going to be using, but that's why some of them are in question marks, and there's certainly some things which aren't even mentioned on that slide. So we are trying to define what problems we're going to have to solve, and then define which tools we're going to have to solve, as well as carrying on supporting the AGRs. And the AGRs are those sort of stations where we get a lot of work from, and that will definitely continue. So the problem we have is to train our existing thermal hydraulics community in the tools we will be using in 5 years' time. I think that will do for today. Thank you.
Thank you, Mike. Our next one is from Ryan Tunstall, Rolls-Royce.
Hi everyone. So unfortunately it's not been possible for us to share any slides, so I thought I'd just spend a few minutes sort of saying what our interests in this are. So I'm the section lead at Rolls-Royce for computational fluid dynamics. We've got a broad interest in sort of the wider computational thermal hydraulics discipline. So we use CFD. We also make quite extensive use of systems code for plant performance analysis. As mentioned by Hector and Mike previously, we've got university technology centres at the University of Manchester and Imperial College London. So typically we're using CFD to model flows within components and subsystems, primarily using RANS analysis, quite often with transient boundary conditions that can be a challenge. We also do some limited LES analyses for high cycle thermal loading, and pretty much all of our CFD analysis now is in Siemens Star CCM+. So from the CCP on the CFD front, I think what we're really interested in is improved V&V, standardized QA processes, as well as sort of benchmarking, perhaps using high fidelity LES, DNS solutions to sort of benchmark RANs and the like that we use more regularly in industry. One of our main challenges as well that we're interested in how we could try and address partly through this CCP is sort of improved acceptance and wider acceptance of the use of CFD and safety justifications. And we're also interested in improved CFD modeling for scenarios like NC and boiling, particularly at the macroscopic scale. As I sort of mentioned as well, we've made quite extensive use of systems codes for plant performance analysis, but we also know that they've got their own limitations. Yes, they're fast to run. You can run them for many, many different scenarios and iterations, but in some circumstances, their assumptions break down. They're not very accurate. On the other hand, we've got CFD, but it's much more expensive. It's more accurate, but you can't often run it at sort of the whole system level. So something else that we're really interested in is bridging that gap between systems codes and CFD. Maybe it's core CFD of a wider system. Maybe it's code coupling. Maybe it's reduced ordered models. So that's something else that we're interested in, particularly for things like natural circulation. That's probably all I've got to say, really.
Okay, thank you, Ryan. The next one is supposed to be Adam Owen from Mortex Energy, but he mentioned he will share a pre-recorded video, but until now, unfortunately, we haven't got a video from him. So we go to our last talk in this section from Husam, Brunel University. Hello, Husam.
Hello. Unfortunately, Professor Hassan Johara has had to leave. We've got another meeting, but we are happy to share the slides with yourselves afterwards.
Okay.
Thank you.
Can you share your slides or?
Yeah, of course, we can share them via email to the whole group while
Okay.
we're doing all the sharing. Absolutely, no problem.
Okay, thank you.
Thanks.
We go to the end of this section. I will hand over to Hector for the discussion section. Hector. Sounds not here.
Hello?
Hi.
Can you hear me?
Yes, is that Hector?
Yeah, well, my internet went down halfway through these presentations. I just managed to get back in using my phone. So I'm a bit out of touch with what's going in between. Have we just finished the presentations?
Yeah, we just finished the presentation.
Okay.
Yeah, we have some.
Now, it will be difficult for me to facilitate the meeting because I don't have any visual. I only have my phone.
Okay, I think.
Yeah, for the moment. Yeah, for the moment, my network has gone down, and we're try to reboot the router several times, but that doesn't come up. So I just thought I couldn't even send you an email. So I can only follow through my phone, but I cannot actually. It wouldn't be very easy for me to facilitate the meeting because I can't see any screens or anything.
Okay, yeah. Professor Shuisheng, you here? Is that okay for you to facilitate the section?
Oh, hi. Do we have? Can you share the list of the questions, please?
Sure.
Right. Okay. Thank you very much for your presentations. I'm sure it's very difficult to actually limit the presentation to 5 minutes. I found that was difficult, but thank you very much, and we're all very useful. And let's try to finish the discussion session relatively quickly, but it's important still. We actually have we have feedback and comments from the general community. And in the past, this is a hugely important part, but this time we have to limit this whole thing. But one way, are you going to share your screen about questions?
I'll send you an email about the questions.
Okay. Okay. It's in my email, is that?
I can share it. Yeah,
it probably will be useful.
I put the questions in the chat.
Yeah.
Okay, that's good. Right. Yeah, probably it's still useful for way to share, but for now, you can see there are 5 general questions. Those are just questions for people to think about, but your questions do not have to limit to any of these. So I wonder whether anyone want to start. Any questions? It could be general questions about the CCP, or any questions to one of the presenters. So
I think we can start from the questions in the chat.
Yeah, we've seen your question way here already. So we've seen, say, number one is general questions, feedback, comments on any of the presentations. Number two is under the current special circumstances, what can the CFD do? And any activities the CFD can organize to support the community. And number three is, do you think regular virtual special topic seminars, workshops, user group meetings useful? Will you attend? Then number four is, how can the CCP help you as a researcher or CFD student? Or lastly, how can the CCP help your organization or yourself as a practical engineer?
Ryan in the, sorry.
Yeah, so eventually I have a question eventually for the CCP project. It seems we kind of going to do a lot of benchmark work on this framework. And I know a lot of people doing the benchmark cases here and there. But is that possible for the CCP to maintain a sharing database or sharing data bank for people or for the other users in the group to do the benchmark or some data analytics?
Right. I'll try to answer this, and probably someone else can come along later. Now, you're right, and actually maintain the knowledge and data within the that has been created by the community, and actually to make use of it later on is hugely important. So you've probably already seen on one of the slides we said we'll use the website to document the database and also the publications generated by this community. And benchmarking is something we were hoping to organize through the years when we basically assess the needs of the community and also the development of the country really, and then organize suitable benchmarking which are relevant to the time and the community. So obviously we open that to international users as well, but the main focus for us is to look at the codes and methodology and the kind of particular reactors we want to look at, and so that people actually work together to share knowledge, and after that archiving, as you say, is actually quite important.
Another thing is about how to control the quality of the shared data. That is, I think that is probably very important, because if we say we're doing the benchmark and these environments kind of biased towards certain mistakes, towards something, we cannot really support that if we're just doing the comparison between the simulated miracle and the experimental data. I think, is there any, can we generate any guidelines about how to generate data?
Anyone want to comment on that?
Yes, Shuisheng?
Yes, please.
Dominic Lawrence here. Maybe it's a bit philosophical, but I'm amazed about the rapid progress of DNS and what Mizari has been doing and NIAMS, etc. I mean, there's no doubt about the quality when you're doing DNS at such a high resolution. And I find it a bit disappointing that so few people are actually interested in using other people's data. I think the first test cases that the NEC 5000 group shared was only used by the Dutch group and the Belgium group. I mean, there was a test case. I don't know if it's spiral wire. It's the same thing with the John Hopkins turbulent database. You know, they have channel flow up to Reynolds 5000 now. And it's so easy to use. I've been trying to get my PhD students to use it for over nearly 10 years now. But it seems all the PhD students are interested in is running their own little LES and little DNS, and nobody's interested in using somebody else's data. And I find this really sad. I mean, we could make much more rapid progress. Why don't we participate? Mizari proposed another fantastic benchmark there. Why is so few people interested in using some, you know, these? The world is now completely global in every area, except maybe turbulence modeling research. Okay, that's my philosophical statement, but think global now, you know, share globally. And we don't need everybody to run their own little DNS, which will be obsolete in 6 months. Let's use this fantastic supercomputing power and the fact that, you know, everything is open now. So that was my comment.
Right, unless anyone else want to comment, my personal view on this is just like any experiment that has been done over the history. You wouldn't be able to generate all the experiments relevant to all designs in one place in one go. So like experiment, I think there are going to be a lot of like research in the high fidelity simulations to tackle their particular problems, and the rock bundle test case generated by through the NIMS system, I agree with you, that was hugely inspiring. I don't think it's just the Dutch people have used. I know they have through the European projects, they actually have a particular branch of their work to collaborate with NIMS program and have done some validations. I know other groups are doing similar things, but not widely published. The same with John Hopkins, database. Often those are used for validation. We, in our group, we actually use that for validation for our simulations. But remember, those are very limited to certain geometries and certain Reynolds numbers. So when you actually move into things that you are interested, I'm sure you have to generate your own thing, in which case actually the overall validation and new efficient kind of software is important.
I think the analogy that Shuisheng makes between validation experiments and the high fidelity simulations is a good one, because if you look at people like the guidance from Overcamp, it's the validation experiment should be designed alongside the analysis it's intended to support. So if there needs to be push and pull. So if you have a problem to solve and you think you can address it with high fidelity simulation, you probably need to then kind of pool the high fidelity into that regime in that domain, rather than it being the high fidelity work being done on simple cases and it being pushed towards who could possibly use it. I think there definitely needs to be an iterative requirement setting and satisfaction in that loop.
I'd echo what Graham said there from our perspective. I think that's very well put. I think there's also some challenges in terms of industry people trying to sort of back up their own work using high fidelity simulations at the minute, in terms of just getting regulators and the like on board with the fact that, you know, a DNS can be as good a benchmark as an experiment?
Let me say something here on, it connects to what Ryan was asking. And so I just want to make clear that, I mean, the reason we perform these large scale simulations is not just for fun. So for instance, some of those large pebble bed cases you're seeing, they are being performed to really, because there is a driver now to improve porous media models for pebble beds. And that's one of the reasons we're performing this. So that to use the full multi-scale stack, going from these DNS calculations, LES calculations, improve RANS models for these particular geometries, which is very challenging, and then go to the to the improved porous media models. That's sort of like the usage of these calculations. So I would agree that in general, like these calculations need to be tied to a need, and it is an iterative process. I mean, you do need more of those. At the same time, though, I do sympathize with the spirit of the comment of Dominique, because we do need more usage of each other's data and act more as a community. I'm not talking just nationally, but internationally too. So that I was hoping that some of these NEA benchmarks would help. I think we need the NEA benchmarks built around DNS data. That's all we need. I think that would be something that can help getting this data used.
Can I just say part of, I think it's Mike Bluck, Imperial, is part of the issue here what the regulator sort of wants. There's the scientific question of using DNS as a means to validate other methods, be it RANS, LES, or whatever that can subsequently be used on things. But certainly in the UK, the desire to use it for thermal hydraulics in nuclear is in large part driven by what the regulator wants and what the regulator trusts, and particularly in regard to sort of accident scenarios, and I think the regulator would say for good reason that benchmarks are all well and good, but they're not necessarily a big part of the jigsaw. I'm just suggesting that's maybe why we don't make as much use of them, as I would agree we should.
Yes, can I just comment? I was interviewed by a think tank from the EU Commission who was noting that there's a lot of enormous collaboration going on in structural mechanics, in materials, etc. And their question was why is research in CFD and terminal modeling so fragmented? Why are they receiving all these proposals from different teams, etc.? Why is there not more collaboration? That was many years ago, and it seems it hasn't really progressed. And there's so much to be done nowadays, just to, you know, for conjugate heat transfer, liquid metals. I mean, there's so much progress we could make if as I said, instead of everyone running his own little DNS in his corner, if there was a really truly global approach to it. We're seeing global collaborations in many areas, COVID, etc., and John Hopkins, and it's just not happening in the CFD and terminal modeling community. I think we're maybe the problem is so hard. Everyone thinks he can make a little dent, you know, wants to have a go at it.
Yes.
Hi, it's Steve Graham here from the National Nuclear Laboratory. I'd just like to reflect on what Mike said and also what Dominique said as well. I mean, I think they both have a valid point to make. I think from experience speaking to the regulators, I think the issue we have that there's some really great fundamental stuff that's being done in the DNS and the LES arena at the moment, but it is quite a long way removed from the actual applications quite often that we've faced with defending in front of the regulator. And I think it's how we make that journey collectively from the research to the position where people who actually use the codes in industry to input to safety cases actually make it count. And I think it's a very valid point that Mike made, and it's all about how we actually do this. Now, it may be that we just need to be better at defending the position, the technical position in front of the regulator.
Yeah.
And we just don't seem to be able to give this the sort of, you know, the input that it needs. It may be quite simple at the end of the day, but we perhaps it's the way we tell the story and the way we bring all these very good concepts together. I don't know.
Yeah, I'd agree.
I agree as well, Steve. I think that's a very important point. And I wonder whether Mike Roberts is still around online. I know that they've tried to support at least some of their safety cases with CFD simulations, and from what I can see, they had to put a lot of effort to justify their means, you know, the method they have to use, even though generally speaking, we proceed the method they've used are quite mature and think that the kind of validation they put together seems to be quite sound. But yeah. I believe that you put a lot of effort for, I mean, it's basically case by case rather than say those methods are good for.
Indeed, I agree with that. Yeah.
Yes, I am here. Yeah, I think when you're trying to present to the regulator, you have to put their hat on.
Yes.
And ask the questions they would ask.
Yeah.
You know, because they're very reasonable people, actually. So it's not a good thing to base your safety case on CFD calculation on its own. You have to present a safety case which has more than one leg, most definitely.
Yeah.
And for example, we've gone to a lot of effort to put thermocouples in reactors, for example, to essentially validate what you're doing. So its validation is the key question that we would ask, and that is the question that the regulator asks. So you have to, instead of presenting a safety case you know is not going to fly, you have to work hard before actually presenting it, and that's the basis of what you have to try to achieve.
Yes. But Mike, thermocouples in liquid lead is going to be very hard.
Yeah, we don't have any of those reactors, so it's not straightforward either putting thermocouples in gas-cooled reactors. I mean, they're fairly hot and high pressure, so no, it's not straightforward by any means. But so it comes down to what somebody said earlier about designing before, you know, designing your reactors even up front to put some good information to give your analysts.
But the kinds of challenges that we have on validation associated with the models that we use in our safety cases, they're not the kinds of problems generally that you would be able to underpin by saying, well, here's a DNS case running at a Reynolds number of 5,000 of a simple channel flow. They're very complicated geometries with lots of rather esoteric features, and those are the kind of the details that we generally have to work hard at, justifying things that you know, there's lots of assumptions in those models about which we have significant uncertainty, and that's where the validation challenges really come in.
Sorry, when I said 5,000, that's a turbulent Reynolds number, okay, based on U-star. So that's about 50,000 or something.
It's still very low.
Well.
You know.
Okay. That was an interesting discussion. Obviously, we haven't finished. We can't finish just today. So hopefully, CCP would be a forum for this kind of discussion. And as also said, we try to use the website to document and so keep some of the progress, you know, joint effort together so that we can actually move forward.